So it's a bit improvised, and I hope I will be able to tell you what we've been working about with Damien, who is also here and couldn't give the talk. So the question is, what happens if you take a manifold and you look at the Laplacian on this manifold, and you pick some eigenfunction of this Laplacian at random? But since I am not a geometer, as Gerard said, there is only one manifold that I know, which is the sphere. Actually, there's two. The second one will come later. So look at the sphere S2 and the Laplacian on the sphere, and you know that the spectrum is composed of things that is discrete. It has lots of multiplicity because the eigenfunctions are given by harmonic polynomials. And so you pick lambda, which is in the spectrum of the Laplacian. You take lambda very large, so you know that there is a lot of multiplicity. And that gives you a linear space, which is a space of eigenfunctions for this particular eigenvalue. And this is a space of finite dimensions, so you can take a Gaussian on this space. So it means that you take uniformly on the, say, on the unit sphere of this eigenspace, you take an eigenfunction. And the question is, can you say something about what it looks like? So if you do that on the sphere, you see something like that. So this is for lambda equals to a few hundred, I think. And the picture is the nodal portrait of this eigenfunction, meaning that the color corresponds to the sign of the eigenfunction. And so you see that you have dark regions which correspond to negative values of the eigenfunction, and white parts which correspond to the positive. And there is an interface between the two, which is the zero set of the eigenfunction. So you take, so phi is in the kernel of this. It's taken uniformly, and the object we want to understand is z phi, which is the set of z's in the sphere, such that phi of z is equal to 0. And maybe also z phi plus, which is the set where phi is positive. So the first questions are kind of local. You might want to consider this picture and look at, for instance, the total length of the interface. Or in other words, if you look at a small domain inside the sphere, what is the amount of action you see in this small subdomain? So what is the local density of length of this interface? So this is the first kind of thing that you might want to understand. These are local observables. So typically the length of z phi, the number of connected components, the way the lines nest relative to each other, things like Betti numbers or whatever. And this is fairly well understood, because if you look at the local structure of this field, well, you can compute everything. You can compute the local variance. You can compute things about the density of zeros on the line. You can look at the curvature of the lines. You can compute many things, because this is a field which is fairly explicit. So it's a Gaussian field. It has a correlation kernel which is explicit. And this is not what we want to understand. The main question that we are asking is, what can you say about the global topology of this z phi? So the typical result that you get if you look at the local structure is that the number of connected components, it satisfies the law of large numbers. So there are many connected components, but most of them are very small. If you look at a typical connected component, it will look like this. So you see there are plenty of them. There are things like this guy, which is a little bit bigger, but it doesn't span the whole portion of the sphere. But the question we are asking is, what happens if you look for large connected components? Can you count them? Can you describe them? Can you say what happens as the degree goes to infinity, as the eigenvalue goes to infinity? And what do you see asymptotically? So as I told you, I know two manifolds, and the second one is simpler, it's the torus. And this is what you get if you look on the torus. So on the torus, everything is even more explicit. So the eigenvalues are of the shape k squared plus l squared. And you pick one with big multiplicity, and you sample in the same eigenspace. And you get something like that, which looks very similar. It has the same kind of feature. It has lots of small bubbles. It has one characteristic length that you see, which is 1 over square root of the eigenvalue in this case. And so this is the same kind of picture. This is a sign of a random eigenfunction of the Laplacian on a torus. And the question is, what do we get if we want to understand the global topology of the level lines, of the zero sets of this eigenfunction? Okay, and here I'm cheating a bit because this is not really on the torus. This is actually on the plane. And what happens is, if you look at a typical eigenfunction, say on the sphere or on the torus, but look at it locally, and then you take the eigenvalue and you take it to infinity, so the things happens at a scale which is 1 over square root of lambda. And if you rescale, you find something asymptotically that is a Gaussian field in the plane, defined in the full plane, and with explicit correlation kernel. So this is the model number 1. That's the limit of eigenfunction in, say, the torus. And this is explicit. It's a Gaussian field in R2. And the correlation function, so the correlation between the value at a point x and the value at a point y, is exactly given by a Bessel function. So it's J0 of the distance between x and y. So it's an explicit field, which is supposed to be universal in the sense that if you take any two-dimensional manifold here with its Laplacian, and you take, so maybe there's no multiplicity of eigenvalues, in which case you don't expect that, but you take a thin slice of the spectrum and you take a random function in this thin slice, then the local behavior should look like that asymptotically. So as lambda goes to infinity and the thickness of the slice goes to 0. So it's universal in this sense that it should describe the local behavior of almost arbitrary eigenfunctions of Laplacian on a two-dimensional manifold. So unfortunately, for reasons that I will try to explain, this is too difficult to address directly with our methods. So we don't know a lot about what happens here in the sense of the global topology of the zero set. So just one more picture in this case. So here is the kind of thing we want to understand. So this is one particular large nodal domain. So in red here, there is one connected component of the set Z plus. And as you can see, it's not microscopic. It spans the whole box. And it looks like it wants to be a fractal set asymptotically if you rescale. You want to say that there is something happening in the limit, that some macroscopic things will exist that will be so macroscopic and kind of complicated and fractal. And so there is a more precise conjecture, and I write conjecture in quotation marks because it's not exactly a conjecture and it's known to be wrong, but to be almost true. And it's due to Bogomolny and Schmidt. And the conjecture says that if you look at large nodal domains like this, it says that it looks like a critical percolation. And here there is also a lot of quotation marks because looks like it's not very formally defined. And percolation, I'm not assuming that you know what that means, so I will spend quite a lot of time telling you what it is and what we can show about percolation and why it's reasonable to expect that it says something about objects like this. So just one last remark about this particular case. This correlation kernel, it oscillates a lot because it's a Bessel function, and in absolute value it decays like 1 over the square root of the distance. So it tells you that this particular Gaussian field is very correlated. It's still ergodic, it still has decay of correlations, but the decay is very slow. And that's maybe the main reason why it's difficult to study, because you cannot expect that there is a lot of independence built in the model, and so it makes the techniques very difficult to control. So that's it for the first model. Any question? Yes?
So is this true if you take a discrete lattice?
I will talk about exactly that in a few minutes. So yes, I will come back to that. And the answer is yes, but we don't know. But yes. Okay, so model number 2. Model number 2 is, so there is something else you can define on the sphere. Instead of taking eigenfunctions of the Laplacian, what you can look at is the restriction of homogeneous polynomials in R3. So here's the second model. What you do is you look at homogeneous polynomials in R3 of degree d, and you want to let the degree go to infinity. So what it means, you take p of x, y, z, which is the sum for all choices of the exponents which are equal to d of, so there will be x to the I1, y to the I2, z to the I3. So these are the monomials, and you want to have something Gaussian because that's nice to have. So maybe you put ai, which are independent Gaussian variables. So again, that's choosing one particular function in some finite dimensional space of functions. And you want to have some geometric interpretation. So for instance, you want the restriction of this to the sphere to be in distribution to be rotationally invariant, because you want this to be kind of universal again. And it turns out that the right way to do it is to normalize the coefficients in a way which I always get wrong, but which is something like square root of, so which one is, so d is the degree, so there is d plus 3 factorial over I1 factorial, I2 factorial, I3 factorial. So this is what you want to put if you want to have the distribution on the sphere to be invariant under the rotations of the sphere. And again, the question is, what do you get if you look at a field like that? So just, yeah.
You also need a symmetry on x, y, z? Or?
So the symmetry is built in the choice of this covariance. That if you map this by some orthogonal 3 by 3 matrix, it doesn't change the distribution of the coefficients. And that's why these are chosen like this. So of course, if you have a field on the sphere, you can always do the stereographic projection and look at it as a field on the plane. And it's still polynomial, and it will be easier to look at. So let's call this p tilde and say p of xy. Now it's not homogeneous anymore. It will be the sum for index sets of sum less or equal than d. And there will be x to the I1, y to the I2, there's still some AI which is a Gaussian. And here there's something like, so the third coefficient will come as a scaling, but essentially there's a constant divided by square root of I1 factorial, I2 factorial. So this is what you get as a field on the plane. And the question is, well, can you look at the structure of such a random polynomial in the plane, and can you say something about its structure? So if you just sample something like that, you find something like this. So this is a typical realization of a polynomial of this distribution. Here the degree is something like 50. And you see that, so again, you can look at the sign of the polynomial. So here one color is positive and one color is negative. And again, you want to look at z sub p, which is the zero set, and zp plus, which is the positive set. So these are the nodal lines, and these are the nodal domains defined by the polynomial. And the question is, can you say something reasonable about this particular set of lines asymptotically as the degree goes to infinity? So let's make the degree larger and see what happens. So if you increase the degree, you see something like that. So again, there is some rescaling to do because a polynomial of high degree will oscillate locally at a scale which is like 1 of the square root of the degree. And here it's rescaled so that this characteristic scale is constant. It's the same as the previous picture. And this is degree something like 200. So here you don't see so much anymore that there's something happening at infinity, because here it looks like it's beginning to be translation invariant. It's starting to look at something local that might be universal. So what happens? Formally, if you let the degree go to infinity, you want to say that there is some phi of xy, which is the infinite degree counterpart of this, which is the sum for I and j positive of, so there is an xi y to the j divided by square root of I factorial j factorial. And there is an aij, which is a Gaussian, and the aij are independent Gaussian of variance 1. So this is a random analytic function now. It's easy to see that the convergence of this is uniform on compact set. So it gives you a random analytic function, which is the limit of these as d equals to infinity. So of course there's a problem, because this is not looking at all like something that is translation invariant. It still remembers where the origin is, because these coefficients, each of them goes to infinity at infinity. But there's one way to make this translation invariant. It turns out that if you multiply this by e to the minus x squared plus y squared over 2, this becomes a function that is a Gaussian field in the plane, and the distribution of this is invariant under the translations and rotations of the plane. So this is our model number 2, which is the limit of random polynomials so they were in S2 or in R2. Okay, so what do you see if you do that? Well, so this is a sample of the limit field. So it's a sample of this infinite sum. And again, what you see here in the picture is the sign of the field. So white and black are positive and negative regions for this field. And you see that it looks kind of, again, complicated. It looks more complicated because there is no clear characteristic length. Before, for the eigenfunctions, well, there was some oscillation, but it was at a prescribed wavelength. Here you want to see details at all scales. There are very tiny connected components, and there are things at larger scales. So again, it's a Gaussian field in R2. And in this case, the correlation kernel of the field is exactly e to the minus x, the norm of x minus y squared over 2. And this is much better for two reasons. First, it's very small at infinity, so there's a lot less correlation in this field. The correlation function decays very quickly. And the second thing, which is actually even more important, is that this correlation field is positive. And you will see why this is crucial in a minute. So this is the model we want to consider, because that's the one on which we are able to prove something non-trivial. And again, this model is universal because essentially, well, there are many setups where you can define a random thing on a manifold of dimension 2. If you impose some symmetry and you impose some complexity going to infinity, you will see in the limit something that looks like that locally. So that's for the motivation, but now I want to speak exactly about this particular random field and see what we can show about it. So the last thing I want to mention is that, again, when you look at this field, you can look at local observables, like the total length of the interface, or the number of connected components, or the nesting, or things like that. And this is, again, well understood, because again, you can compute. The kernel is explicit, and everything can be computed in terms of this kernel. But the questions we are interested in are about the global behavior of the field. And if I do the same operation as before, so this in red is one particular connected component of the Z plus set. So it's one large nodal domain. And again, you can see that this spans the whole width of the box. And it has some inner structure. It has holes at many scales, and it's a complicated set. And again, this is something that you don't see if you just count the number of connected components, or if you look at local observables, because it's something to do with the global topology, which you miss if you just focus at the field locally. So this in red is really the object we want to understand. We want to understand what happens if you look at the large connected components of the set Z+. Okay, and then the conjecture is essentially the same. That it should look like critical percolation. And again, I will tell you more specifically what it means to look like critical percolation and what kind of thing we expect. Any question? Okay, so this was part one of the talk, the definition of the objects we want to look at. Now, I will give you a 15-minute crash course on percolation, because maybe some of you have not heard about it. And it's a nice probabilistic model. It's one of the simplest probabilistic models. And it has a lot of open questions. But still, a fair amount of technology is known that we will want to import from percolation to the study of these random analytic functions. So what's percolation? So this is a sample of Bernoulli percolation. So to define percolation, what you do is you start from your favorite lattice in the plane. So here, this is on Z2. But you can change the lattice. You can take the hexagonal lattice, the triangular lattice, anything periodic will do. And what you do is for each edge of the lattice, you toss a coin, and with probability p, some parameter, so p is between 0 and 1. And for each edge, you choose randomly if the edge is open or closed. And you do that independently for different edges. So this gives you a random subgraph where you keep all the vertices and you keep all the open edges. So it gives you G sub p, which is a random subgraph of Z2. So this is what you get if you sample it for p equals to 0.3. So you see that this random subgraph has lots of atoms, and it has a fairly small connected component. And it has, well, kind of larger connected components, but there's nothing spanning the whole size of the box. And the main question is, what is the connectivity structure of this random subgraph? And the quantity that is natural to look at is theta of p, which is the probability that if you look at G sub p, this random subgraph, and you look at the connected component of 0, you look at the probability that this component is infinite. So it's the probability that 0 is connected to infinity in GP. So this is a function of p. It's a non-decreasing function of p, because if you increase p, you will open more edges, so you will make the connected components of GP larger. And so it's a function, and if you look at the graph of this function, so this is 0, this is 1. If you put p equal to 0, theta is 0, because everything is formed of atoms. If you let p equal to 1, everything is connected, so theta of p is 1. And it turns out that there is a critical parameter, Pc, such that theta is 0 up to Pc, and then it's positive and going to 1 as p goes to 1. So this is what you should expect if you look at these random subgraphs for different values of p. Okay, and here I'm cheating a little bit because I drew that continuous, and it's kind of an open question in general to show continuity at the critical point. But in Z2, it's known that it's continuous. So let's do a little simulation. This is p equal to 0.3. If you increase p, you see that some of the clusters merge. But here, if you look at the picture for a long time, you will not see spanning clusters. And again, if you increase p, you will make more and more things connected until something happens, in this case at p equal to 1/2. And this is the first time at which you see connected components that are at the scale of the box. So here, I think there is nothing spanning horizontally, but there should be one spanning vertically. And if you can find it, you have good eyes, but it's starting to behave at the scale of the box that you're looking at. So of course, there are still atoms, because each point is an atom with probability 1 minus p to the 4, so it has positive density of atoms, but there are large things happening. And then if you increase p a little bit, then you see that mostly you get a connected graph. So this is 0.6, and this is 0.7. And now this one is almost connected. It has one giant component spanning everything, plus a little bit of dust in the holes, but not a lot. So in Z2, the Pc is equal to 1/2. So I want to tell you why this is true, because that's one of the key ingredients in what we want to do with random analytic functions. So I want to tell you why it's natural that something should happen at p equal to 1/2, and then going from this remark to proving that this is actually the critical point. Historically, it took 10 years, and it was done by Kesten in the 80s. But the key remark is something very simple. So here's tool number 1. Tool number 1 is known as planar duality. So what's planar duality? Well, if you have a graph that is drawn on the plane, so here is Z2. So this is your graph. What you can define is a dual graph which has one vertex in each face of Z2. So these are the vertices of the dual graph. And it has an edge if and only if the two corresponding faces are adjacent in the initial graph. So these are the edges of your dual graph. And there are also edges like this. So that's not very exciting because the dual graph here is isomorphic to Z2. But in retrospect, that's very exciting because essentially it tells you that Z2 is its own dual, and that when you have something that is self-dual, you can hope that you can compute things. So this is a dual graph, and what can you do on the dual graph? Well, if you have a percolation configuration in the initial graph, so let's say that these edges are open, something like that. What you can do is build a configuration on a dual graph by declaring that a dual edge is open if and only if it does not intersect an open edge in the primal graph. So this is a dual configuration. It has these edges. So the probability that a dual edge is open is the probability that the primal edge is closed, so it's 1 minus p. And these are independent because you only look at your dual edge locally, and there is no dependence coming up in the construction. So the dual model, it's a percolation on Z2 star on the dual graph with parameter 1 minus p. And the second thing is, if you have a large cluster in the primal graph, like this, and you look at the dual picture, well, the dual clusters will be surrounded by the loops of the primal cluster, so they cannot be large. And vice versa, if you have no large loop in the primal one, then the dual will be able to span. And so it tells you that it is not possible for the model and its dual to be supercritical at the same time. They cannot both have an infinite cluster. So it tells you that the critical point has to be the dual, the self-dual point. It has to satisfy that PC is 1 minus PC, because that's the only place where you can switch from one behavior to the other behavior. So this implies that PC is 1 minus PC, and if you solve this equation, you find a half. And that's why PC is a half. So I'm cheating a lot here because there's one other thing that you need to prove. It's quite possible that none of these two models have an infinite component. And they all have loops at all the scales surrounding each other, but none of them is infinite. And what you want to show, if you want to prove that this is true, is that this coexistence of finite loops cannot happen at several values of p. And that's the part that took 10 years to prove. So if you want, the upper bound on the critical point is just obtained by topology, and the lower bound, this requires some probability. Okay, so the thing that you should keep in mind is that there is planar duality, and planar duality helps you control the probability of some events and gives you a hint that 1/2 should be special. Okay, for instance, and I still want to keep the screen because there's one last thing I want to show on the screen. So one corollary of the planar duality is this. So corollary. If you take a large box of n by n, like this, and you look at the event that there is a path spanning from left to right in this box. So this is the probability. And from now on, I will only look at critical percolation, so at p equal to 1/2. So I'm not writing p in the notation anymore, but you should think that it's 1/2. And you look at the probability of this event, that there is a path spanning from left to right. So can you tell what the probability of this event is? That's the one thing you should remember for the talk. It's the one thing that is completely universal in what I'm talking about, and it's the reason why things are nice for percolation. So what could prevent the existence of a left-right crossing of this box? Well, it's the existence of a vertical dual crossing. And that's a vertical crossing of a square by a model which is the same model. It's percolation at parameter 1/2. So it has the same probability. And so you have a partition of the whole configuration space into two sets of the same probability, the ones with horizontal crossing and the ones with a vertical dual crossing. And so it tells you that this probability is equal to 1/2. And that's an exact result that does not depend on the size of the box. And it's true as soon as you can do some duality argument like this. So for instance, if you go back to any of these Gaussian fields that I had, there is the same duality. Instead of the graph and dual graph, you have the duality between the z plus and the z minus. And the thing that can prevent a horizontal positive crossing is a vertical negative crossing. So that tells you that in any square, the probability that there is a nodal domain crossing from left to right is identically equal to 1/2. And that's a uniform bound, and it tells you already something non-trivial about the large connected components, because it tells you that it's reasonable to expect that they exist, because in any square box, you will see one with probability 1/2. Okay, so this is the first thing that you get from percolation, from planar duality, and from these kind of considerations. So tool number 2. So if you want to look at something that is macroscopic, it's not enough to cross squares. You want to cross other kinds of regions. So for instance, rectangles. And if you want to control the probability that if you take a rectangle of 2n by n, it's crossed horizontally, you don't get anywhere using duality. Just duality will not give you any estimate, except that this probability is 1 minus the corresponding probability in the other direction, but that's it. So tool number 2 is known as the Russo, Seymour, and Welsh theory, or technology, or whatever. It's a whole construction, and the main output of the construction is that if you take a rectangle of size n by lambda n, and lambda is fixed, it's the shape of the rectangle, but n is going to go to infinity, and you look at the probability that there is a crossing, then this probability is between epsilon lambda and 1 minus epsilon lambda for all n. So the statement is whenever you fix lambda, there is an epsilon lambda positive, such that these crossing probabilities are uniformly bounded above and below by something non-trivial. So if you want, epsilon sub 1 is 1/2, but this epsilon exists for every value of lambda. So this tells you that not only you cross large squares, but you can cross arbitrarily long rectangles of fixed aspect ratio with probability that does not depend on the scale. And this is something that is really non-trivial. It's something that we know how to prove in a few models, including Bernoulli percolation on the square lattice. And it's believed to hold in the much more generality, but we really don't have a robust proof of such estimates that would work in more generality. Yes?
That thing there, do you know what epsilon is more or less?
Ask again in 10 minutes.
Okay, I'm sorry.
I will tell you. Again, the answer is the same. We know, but we don't know how to prove it in this case, but we know in a triangular lattice. Okay, so how do you prove something like that? And I will show you the proof in the case that lambda is 3/2, so something strictly longer than a square, but not too long. And going from 3/2 to arbitrary lambda is the easy part. So the really difficult part is to build with positive probability a crossing of a rectangle which is not a square. So here is what you do. So remember, we only have one tool at our disposal. We know that we can cross squares with probability 1/2. And we want to build crossings of large rectangles with positive probability. And you need to be clever because it's not just so just one picture that I want to put to convince you that it's non-trivial. So the first try you might want to try to cross a rectangle of 3/2 by 1 is this. You have this rectangle of 3/2 by 1. You know how to cross squares, so you cross the first square here. You cross the second square like this. It also has positive probability. And you want to join them by a vertical crossing of some square. So let's say the square in the middle. And maybe you're not lucky. Maybe your vertical crossing is like this. So it does not connect. And you can put as many squares as possible. It's always possible topologically to have non-touching crossings like that. And if n is very large, the complexity of all the pictures that you can get explodes, and that's why you need some more ID than just crossing squares. And that's why we cannot prove Rousseau-Seymour-Welch for all the models that we would like. So here's one proof. So the 3/2 by 1 rectangle that we want to cross is the size of the screen. And so this small square here is this middle square down there. So we know that with positive probability, we can cross it vertically. So this costs you probability 1/2. Okay, once you have this, what you can look at is the rightmost crossing. So this is the rightmost crossing, vertical crossing in this box, which exists with probability 1/2. And saying it's the rightmost crossing tells you that it is a crossing. There is no crossing to the right. So in this region here, you have some information saying that there is no vertical crossing. But it tells you absolutely nothing about what happens in this region. Because you can change anything here, it will not change the location of the rightmost crossing. Okay? And now you draw in your head the symmetric of this rightmost crossing in the upper half. And this gives you some symmetric domain, which is shorter than a square and with a complicated boundary. But it's shorter than a square. So if you cross the square in particular, you cross this domain. So you cross this domain with probability at least 1/2. And because it's symmetric, you land on the bottom with probability at least, again, 1/2 conditionally on the fact that you cross. So at least 1/2. So again, with positive probability, you have a path like this. Okay? So the outcome is you have some structure like this with probability something like 1/8, at least 1/8. Okay? And now, so the blue one is the one we just built. The green one is the symmetric one. It also exists with positive probability. And the red one is just crossing a square horizontally. So we have these three events. And if we have all three of these events, then they collaborate to make a crossing of the horizontal box. So there is one thing that we need to make this argument work, and it's called the FKG inequality, which is saying that these events, they are certainly not independent because they involve the same edges, but they are positively correlated. So they are increasing events in the sense that if you open more edges, they are preserved. And FKG tells you that increasing events are positively correlated. Meaning that if A and B are increasing events, then the probability that A and B occur at the same time is bigger than the product. So in the case of a product measure, this is known as the Harris inequality, and in more general models of statistical mechanics, it's known as the FKG inequality. And if you have never seen that, there's a nice exercise saying that if you have f and g from R to, say, 0, 1, and mu a probability measure on R, then the integral from minus infinity to plus infinity of fg d mu is bigger than integral of f d mu, integral of g d mu. And these are, of course, they are non-decreasing. So this is the baby version of the FKG inequality. It's the case where there is only one totally ordered space, but it's a nice inequality. And this is just a generalization of this by tensorization and something. Okay, so FKG is essential if you want to obtain something like crossing probabilities. And so we want to have something like that for our Gaussian fields. Because if we do, then it will tell us something about the large-scale behavior of the nodal domains. And it turns out that for a Gaussian field, the FKG inequality is true as soon as the correlation kernel is positive. And that's why the e to the minus distance squared over 2 correlation kernel is nice, because it's positive, so we will have the FKG inequality. And the first one with the random eigenfunctions, it is not positive, so this fails, and essentially everything fails. So it doesn't decay fast enough, and besides, it's not positive. So it has all the bad features, making the model more difficult. Okay, now just one last remark about percolation, and then I'm going to tell you what we are able to prove for these random analytic functions. It's answering your question. So the main conjecture is the following. If you take any simply connected domain in the plane, omega, and any two boundary arcs of this domain, and now this domain is fixed, and you look at percolation on a very fine copy of Z2. So you look at delta Z2, and delta is going to go to 0. And you look at the probability that at the critical point there is a crossing between these two boundary arcs. So this is uniformly bounded below, because if you know how to cross rectangles, you can make a path out of rectangles that will be crossed with positive probability and imply the existence of this crossing. So this is bounded above and below, and the conjecture is that this converges to some function of the domain and the boundary arcs. And moreover, this function is supposed to be conformally invariant, meaning that if you have another domain, omega tilde, with again two boundary arcs, but where this domain is conformally equivalent to this one, so meaning these 4 points have the same cross ratio or something like that, then the limit is expected to be the same. And so, to give some explicit value for the limit, it's expected that if your domain is the equilateral triangle of size 1, and your boundary arcs are this one, and this length is x, then the probability in this triangle that you have a crossing as the mesh goes to 0, this converges to some function of the domain and the arcs, which then is a function of x. And it's very difficult to guess, but it's true that the limit is expected to be x. So this is the big conjecture about percolation, that if you take any domain with 4 marked boundary points, if you want to compute the limit of the crossing probability, what you do is you map the domain conformally to the equilateral triangle, and you measure the length of delta 2, and it gives you the limit of the crossing probability.
So
So this is done for side percolation on a triangular lattice. And that's the big result of Smirnov, to show that this actually holds for side percolation on a triangular lattice. And it's open for the model I described of bond percolation on the square lattice. So what I mean by the nodal domains should look like percolation, really you should interpret it as if you take any domain in the plane and you look at one of these random analytic functions in the domain, but you rescale it by a factor delta, then the probability that there is a path where a field is positive crossing this domain, first it's bounded above and below, and second it converges to something that is conformally invariant and which is the same as for percolation. So the conjecture is this holds also for random analytic functions. So this is not exactly what Bogomolny and Schmidt claim, but it's compatible. And the main thing that we are able to show with Damien, it's this. So that's the theorem. And the theorem is that Rousseau-Seymour-Welch estimates hold for model number 2. So more formally, if you take P of xy, which is this sum of x to the I, y to the j over square root of y j factorial times aij, ij positive. If you take any omega which is simply connected, and you take any delta 1, delta 2 which are boundary arcs of omega, and you look at the probability that there is a component of zp plus intersection with the rescaled version of omega, so k omega, spanning between k boundary 1 and k boundary 2. So you fix your function, you fix your domain, but you rescale it, and you look at the probability that there is a component spanning from left to right, then this is bigger than some epsilon depending only on omega delta 1, delta 2, uniformly in k. So there is epsilon positive such that this happens. And so once you have that, you can look at all the papers on planar percolation, and this can be exploited to give some very nice estimates. And to give just one of them, if you take your random analytic function and you restrict it to the upper half plane, and you want to estimate the probability that from two neighboring points here up to radius r, there is one line where the function is positive and one line where the function is negative. Something like that. Well, this probability is up to constant equal to 1 over r. And this is just a consequence of Rousseau-Seymour-Welch estimates. So you get very quantitative things that are really non-trivial from the point of view of the function, but that you can compute using Rousseau-Seymour-Welch. If you want just one of them, it's expected to decay like 1 over r to the 1/3, but this requires more than Rousseau-Seymour-Welch. It requires the convergence here, which we don't know how to get. So if I have 2 minutes, I will give you just one word about the proofs and why it's difficult and why it's doable. So first, why is it difficult to extend the proof that I showed you of Rousseau-Seymour-Welch in some case like that? So the field that we are considering has two features that make it difficult. The feature one is that it's correlated. So if you know the field somewhere, it will give you some information quantified by the correlation kernel. So it's not very correlated, but it is correlated, and it makes some arguments fail. But the main obstacle is that it's analytic. So what it means is that if you know the restriction of the field to any open ball anywhere, it gives you the whole field. You can compute everything. And so you cannot really condition the field on what it does somewhere and expect that it will be independent somewhere else because of analytic continuation. So for instance, if you remember the argument, we had something like that. You look at the vertical crossing. So far it's fine, it's probability 1/2. And then you want to look at the rightmost vertical crossing. So in the case of a random function, the rightmost vertical crossing, well, it will be a line of zeros of the function. And if you know the shape of a line of zeros, that's enough to rigidify the thing and prescribe the behavior of the function everywhere else. That's just enough information by analytic continuation. And so you cannot proceed from there because you wanted to have something independent in this symmetric domain on the left, and you don't have that because it's an analytic function. So the solution that we do is that we discretize the field on a lattice. So we have this function on the plane. It has some complicated picture of level lines. And on top of the picture, we put a very fine grid. And what we do is we look at the sign of the function on the vertices of this grid. And the whole point is that you need to choose the mesh of the grid in a proper way, and that's all the technical points of the paper. If the grid is too wide, then knowing what happens on the grid, which then boils down to percolation, will not be enough to catch the combinatorics of the field itself, because you might miss a loop if it goes between 2 points of the grid. So you want the grid to be fine enough to catch all the combinatorics of the field. But on the other hand, if the grid is too fine, then you will hit the analytic properties of the function, and it will not have decaying correlations. So you need to find the mesh at which you discretize the model just at the right scale to have, at the same time, nice correlations, no harm from the analytic feature of the function, and enough information about the topology. And that's what we are able to do. OK, thanks.